So we had started talking about intermolecular forces, and there were three of them, right? Which we said that there are three weak forces between molecules, and one of them was permanent dipole. You got hydrogen bonds, and you got van der Waals forces or instantaneous dipole induced dipole. So you had these three forces, and we started off with the first one, which was we started off with permanent dipoles. That in permanent dipoles, we said that the electronegativities of atoms, we discussed that atoms become more electronegative when you move towards the right, especially this corner. And we discussed that when you move to the right, you got more protons, so there's more attraction for electrons. And when you move up the group, you got a smaller atom which is less shielded, so it's going to attract its electrons more strongly. So ये सारा था, और फिर था we discussed that if you have a covalent molecule, then what happens in a covalent molecule is that the electrons are always, when there's a difference in electronegativity and one of the atoms is more electronegative, the electrons are closer to one of the atoms compared to the other one. So which is why that results in an unequal distribution of electrons in this particular bond. So there's a lopsided distribution. The electrons are closer to this Cl, which is why it's got a slight negative charge, while the other one is going to have a slight positive charge.
Which topic are we studying today, sir?
ये हम वो कर रहे हैं intermolecular forces. ठीक है?
Okay.
We'll cover intermolecular forces and do its questions. ठीक है? अच्छा, so this one, the first one, permanent dipole. So whenever you have a molecule and there's a difference in electronegativity, you get a permanent dipole. The electrons are closer to one of the atoms. So you got two poles, one positive, one negative, just very slightly negative. And the molecules are going to attract each other. So there's going to be this intermolecular forces that's going to exist, and that would be known as a permanent dipole interaction. अब इसमें ये कि you need a difference in electronegativity. Firstly, if there is no difference in electronegativity, that means there would be no dipole. So no difference in electronegativity results in no dipole. That obviously means no dipole. So one example is you got a fluorine and fluorine atom. The electrons would be evenly shared. To get the electrons, this fluorine is pulling electrons. This other fluorine is also pulling electrons with pretty much the same force. So the electrons are kind of equally distributed. So they are equally distributed, and there's absolutely no permanent dipole. There is no side which is positive. There's no side which is negative in this particular case. So then there's another scenario, and that is, they're formed when there's a difference in electronegativity, but they're also dependent on the shape of a molecule. So permanent dipoles get cancelled out depending on the shape of the molecule. Just hold on one second. So this one, coming back to this, they get cancelled out depending on the shape of a molecule. So the thing is, we need to learn how to figure out the shape and how are they dependent on the shape of the molecule. So how do you figure out what the shape of the molecule is? So the shapes of molecules can be figured out by simply looking at how many bonds and how many lone pairs they have. So for example, you've got an atom which has just 2 bonds or 2 pairs of bonds. The idea is that these bonds, they repel each other. So you got electrons on this side and you got electrons on the other side, and these electrons, they all repel each other. So the point is that if you have a double bond on the right side, the other double bond is going to be on the extreme left side. It's not going to be like this, that the 2 double bonds are close to each other. They're both repelling each other. So the shape of the molecule is dependent on this mutual force of repulsion that exists. And that's known as the valence shell electron pair. It's known as VSEPR, which you don't really have to remember what that stands for, but it simply means that valence shell electrons it's electron pair repulsion theory. So it means that all the bonds and all the lone pairs, they all try to be as far away from each other as possible. And whenever you see a molecule, you can figure out the shape of the molecule based on that. So starting with the first thing, that when you talk about shape of a molecule, the first thing is that you should remember or learn how to count lone pairs and bonds. So if I have a molecule, any molecule, just once again. So if I have this molecule, the first thing is you can figure out the number of bonds around the carbon atoms. You can figure out the number of bonds around the oxygen atom. It's always the central atom that you should look for. But the thing is, lone pairs are never shown. Lone pairs are basically your electrons in the outer shell that are not involved in bonding, or orbitals in the outer shell that are not involved in bonding. So how do you figure out the lone pairs? And the lone pairs are never written. The bonds are always clearly, you can always clearly see the bonds, but the lone pairs are never shown. So the way you tell whether an atom has electrons that are not involved in bonding is by looking at the group number. For example, if carbon is in group 4, you know that it's got 4 valence electrons. the group number tells you the number of valence electrons it's got. So if carbon is in group 4, you can quickly tell how many valence electrons it's got. It's got 4 valence electrons, and all 4 are bonding at the moment. So that means there is nothing left. I mean, all 4 electrons, 1 electron is bonding over here, 1 over here, 1 over here, 1 over here. So it's got no lone pairs. But if you look at oxygen over here, oxygen is in group 6. So since oxygen is in group 6, it's got 6 valence electrons. Now, if it's got 6 valence electrons, only 2 bonds are being made. One over here, so 1 electron gets used up in one of the bonds, the other one gets used up in the other bond. So out of the 6 electrons, only 2 are actually taking part in bond formation. So that means they're going to be 4 electrons or 2 lone pairs that would be left. That would absolutely not be doing anything. So every time you have to figure out whether a molecule has or an atom has lone pairs or not. So these lone pairs, they need to be found out. They're never drawn. Most of the time, they're never drawn in a molecule. You have to figure them out on your own. So for example, if we do another example and we try to count the lone pairs and the bond pairs in a molecule, then so let's do one more example. Let's so let's think of this molecule now. And I'm going to count, I mean, the bonds are clearly visible to me. The lone pairs are not. So nitrogen is over here in group 5. So that indicates it's got 5 valence electrons. So it's only making 3 bonds. That means out of the 5 electrons, 3 are actually taking part in the bond. 2 of them are not being used. So that means there's 1 lone pair. Carbon over here is in group 4. So that indicates if it's in group 4, that means it's got 4 valence electrons. So it's making 4 bonds. So all 4 are taking part in the bond. Oxygen is in group 6. It's got 6 valence electrons. It's making 2 bonds. So that means 4 electrons or 2 lone pairs are still left. Carbon is in group 4. So all 4 are taking part in the reaction. So that means there's nothing left. So the first thing is you have to figure out the lone pairs in the atom. The next thing is trying to figure out the shape of a molecule. What's important is the shape is always determined by the central atom. It's not determined by the atom on the edges. It's always determined by the atom that's right in the middle, like carbon over here, or like oxygen over here. Even oxygen is somewhere in the middle. So the shape is not determined by the atoms that are lying on the edges. The arrangement is always around the central carbon atom. So the first thing is you have to figure out the shapes. Now there are 3-4 basic shapes which a molecule takes. The rest are just derived from those shapes. So we're going to just quickly do those shapes. So if an atom has 2 bonds, the shape is obviously linear. There's going to be 1 bond over here. So that's going to be your Y. And there's going to be another bond on the other side. So that's the first basic shape. And this one is linear. And the angles are 180 degrees. Linear means the atoms would be arranged in a straight line. Similarly, if an atom has 3 bonds, so the shape is going to be fan shaped. It's going to look like a fan. The bonds are going to stay as far away from each other as possible. And all the angles are going to be 120 degrees. So it's going to be all the angles would be 120 degrees, and this is going to be trigonal. So this one is going to be trigonal planar. That means it's fan shaped and it's planar. A fan is a completely planar two-dimensional thing. There's no bond coming out of the page. There's no bond going into the page. It's lying completely flat on this page like a fan. So whenever you see an atom that's making 3 bonds, that's the shape. Then you have the next one. So the next one is if an atom has 4 bonds, then for 4 bonds, the shape is tetrahedral around that particular atom. A tetrahedral shape is a 3-dimensional shape. So a tetrahedral shape is so that's what a tetrahedral shape looks like. It's a very symmetrical shape. All the angles are exactly the same. So this is what a tetrahedral shape in 3-dimensional looks like. And it's a very symmetrical shape. You can turn it around. All the angles are exactly the same. They're all 109.5. All the 4 bonds are going to stay as far away from each other as possible. So that is what a tetrahedral shape is. And the angles in this case are 109.5 degrees, all of them. Between any 2 bonds, the angles are 109.5. Then an atom can have 5 bonds. If an atom is making 5 bonds, the shape of 5 bonds would look like this. That it's going to have, so 5 bonds is going to look like this, that there's going to be a fan-shaped arrangement in the middle. So think of a fan that's lying completely flat. And there would be one bond, and this is a 3-dimensional shape as well. There's going to be one bond that would be coming on top out of the fan and one hanging at the bottom of the fan. So think of a ceiling fan that's and there's one bond that's hanging at the bottom and one bond that's right on top of it. So there would be 2 atoms attached to those places as well. Now in this case, this shape, but this particular shape is known as a trigonal pyramidal arrangement. Pyramidal arrangement, and the angles between the fans are 120 degrees, and the angles that the bonds that are hanging at the bottom and the top of the fan, they're making an angle of 90 degrees. So that is 5 bonds. So if an atom makes 5 bonds, this is what it's going to look like. And then you have 6 bonds. What if an atom has or a molecule has 6 bonds? So the shape for 6 bonds would be like this. There would be an atom in the middle, and there would be bonds all around it. There would be a bond on the right side. If there's 6 atoms attached to it, there would be a bond on the left side. There would be a bond that would be on top. There would be a bond that would be at the bottom. There would be a bond that would be going behind it. There's going to be a bond that would be coming out of it. So that is known as an octahedral shape. And in that case, all the angles are going to be, they're all going to be 90 degrees. So that is what an octahedral shape would look like. So you've got these 5 or 6 basic shapes. First one, if an atom has just 2 bonds, that particular shape is linear. It's 180 degrees. If an atom has 3 bonds, it's going to look like a fan. It's going to be called trigonal planar. If an atom has 4 bonds, it's going to be tetrahedral, and the angles are going to be 109.5. And if there are 5 bonds, it's going to be trigonal pyramidal. A fan in the middle, a bond hanging on top and at the bottom of the fan. And 6 bonds would be octahedral. One top, one bottom, one right side, one left, one behind it, one in front of it. So all the bonds, they hate each other. They try to repel each other, and they try to be as far away from each other as possible. Now, the thing is that there would be some derived shapes as well. And those shapes are that what if they're not just bonds? Let me just adjust this. As I said, so derived shapes. The first one is for trigonal planar. Sometimes what will happen is that the arrangement around the central atom, it's not just 3 bonds. Instead, let me just copy paste this. So instead, the shape is like this. That on this side, there is no atom attached, but there are electrons. And those electrons, I mean, the lone pairs of electrons. Instead of a bond, you do have electrons, but there's a lone pair. So you've got 2 bonds, and you got a lone pair on the other side. So the electrons are still there. I mean, you still have electrons, but there is no atom attached to it. So it's exactly the same shape. Everything kind of remains exactly the same, except for the fact that one of the sides is missing now. You've got electrons there, but there's nothing attached to those electrons. That is what lone pairs are. Lone pairs are electrons in the outer shell that are not taking part in the bond. So it doesn't matter if the electrons are bonding or if the electrons are not taking part in the part. There are electrons there. So the shape kind of remains exactly the same, except that there's nothing attached on one side. So it's like a fan with one side missing because there's nothing attached over there. This shape is now no longer going to be called trigonal planar. Instead, it's going to be called bent or V-shaped. Or you can also call it a non-linear shape. And one important point is that these lone pairs are always closer to the atom because they're not getting pulled by some other atom. They're not being shared, so they're always closer to the atom, which results in greater repulsion. So the lone pairs kind of repel the other bonds slightly more, which is why the angle kind of decreases. And instead of being 120, it actually decreases to somewhere between 117 to 119 degrees. So remember this, lone pairs are always closer to the atom because they're not getting pulled by some other atom on the third side. So which is why the angles kind of shrink. So in this case, the angle would shrink to 117 to 119. So remember this, you can have 3 bonds. That's going to be a perfect fan. It's going to be trigonal planar. You got 2 bonds, and on the third side, you got a lone pair. You still have the same arrangement, except there's nothing on top. So it's just a V. It's just a bent molecule with the fan missing the top side. And the lone pair are closer to the atom, so they're going to create more repulsion. So remember this point that, and I'm going to add this point over here at the top. which is that lone pairs always exert more repulsion compared to bonds. So, Sara, clear? Is this clear? Hani, is this clear, Sidra? Mahad?
Yes.
So, is this clear? Next one is the tetrahedral shape is going to have many different versions as well. Because, 1 second. Achha, so the tetrahedral shape can have many different versions as well. Remember, if you have 4 pairs of electrons, there's a bond pair, bond pair, bond pair electrons over here. They're going to be as far away from each other as possible. So it's going to be a tetrahedral arrangement and the angle would be 109.5. But you don't always have bonds. Sometimes what will happen is, so this one is going to have 3 different versions. Let me just shrink it a bit. So this one over here is going to have, so let's say this is the first one. And this here is the next one. So it's going to have 2 different versions actually. So again, in this case, sometimes what will happen is instead of an atom having a bond, it's going to have lone pairs on one side. And there's no atom attached to that side. I mean, there are electrons there, but there is no atom attached to it. So what will happen is that the top is missing. So it's like a tetrahedral shape with the top missing. So it looks like a pyramid now. You just have a 3-sided pyramid. So this one is no longer going to be called tetrahedral. Instead, it's going to be called a 3-sided pyramid, which is trigonal bipyramidal. So it's going to be called trigonal bipyramidal. And the lone pairs are closer to the atom because they're not getting pulled by some other atom. So they're going to exert greater repulsion, which is why the bonds are going to be closer to each other, which is why the angle would slightly shrink by approximately 1.5 degrees, and it would instead now be 107. So these 2 shapes, the tetrahedral shape and this trigonal bipyramidal shape, are kind of the same shape, except that the top is now missing. You still have electrons there, you got a lone pair, but you don't have anything bonded to it. So you got electrons there, nothing bonded to it, so the top is now missing. Similarly, this one, again, sometimes what would happen is that there would be 2 sides missing. Instead of atoms being attached to those 2 sides, they're going to be electrons, just electrons, lone pairs. So there's just going to be electrons there. So again, it's obviously, I mean, there are 2 sides that are missing now. So the shape of the molecule is just this. It's X bonded to Y, X bonded to another Y. So that's it. I mean, these 2 sides, there's nothing attached to those sides. So this one is just going to be V-shaped. It's just going to be bent or non-linear. So it's going to be V-shaped or bent or non-linear. And because of the greater repulsion by the lone pairs, the angle between the bonds is going to shrink even further now. Pehle to 1.5 hua tha, now it's going to go all the way down to 104.5 degrees. So it's going to shrink even more because now you've got 2 lone pairs. So remember, 4 bonds, the shape is going to be this one. If you have 3 bonds with 1 lone pair, it's going to be trigonal bipyramidal. And instead, if you have 2 lone pairs and just 2 bonds, then it's going to be V-shaped. So for 5 bonds, there are a number of variations, but I mean, it's a lot harder to remember those, and they've never actually been asked. And we can also talk about 6 bonds. There would be some variations which have been asked, so we can talk about them. So the other variation that we can get is, so this is octahedral. So instead, what we can have is, in this particular variation, you would have 4 bonds, and they're going to be 2 lone pairs. So on 2 sides, behind it, and in front of it, you got lone pairs. So that means the front side and the back side are missing now. So it's just a planar molecule because there's nothing behind it, just electrons there. And there's no atom attached in front of it. So just electrons over there. So this is going to be called a square planar shape or arrangement. Why? Because it's no longer 3-dimensional. It's just one bond on top, one on the right side, one on the left side, one on the bottom side. Nothing in front of it, nothing behind it. So there's nothing in front or behind it. So it's just going to be square planar. The angles would still be 90 degrees. They're going to still be exactly 90 degrees. So you have to remember all of these shapes, and I'll send a sheet which has all these shapes. So by looking at an atom, so by looking at the atom, one second. So by looking at the atom, you can figure out what the arrangement is by looking, for example, if you look at this carbon atom, and remember, it's always focus on the central atom, not the side ones, the middle one. If you focus on this carbon atom, it's got 4 bonds around it. So if it's got 4 bonds around it, the shape would be 4 bonds. The carbon atom would probably in 3-dimensional would look exactly like this. Similarly, if you've got this carbon atom, and remember, think of double bonds as one thing. It's basically one pair of electrons over here. There's a pair of electrons over here, and there's a pair of electrons over here. So there's 3 pairs of electrons. So remember, always think of double bonds as one thing because the double bond is together. So it's 3 pairs of electrons or 3 bond pairs. One bonded pair is over here, bonded pairs over here, bonded pairs over here. So that is 3. So that's going to be fan shaped. If you have 3, that particular molecule is going to look like this. Around that carbon atom, the arrangement would be fan shaped. Then you have this nitrogen atom. It's got 1 lone pair and 3 bonds. So it's going to look like this. The nitrogen atom would be sitting at the bottom with a lone pair on top and the 3 bonds arranged in a pyramidal manner around it. So we're going to practice this and
Sir,
yes.
but would the trigonal planar one have 2 lone pairs because of nitrogen and oxygen?
Which one?
You see on this thing, yeah, there's the O has 2 lone pairs and the N has a lone pair. So would the trigonal planar one have 2 lone pairs?
Listen, I'll just draw this quickly. What you just have to focus on is, I think we'll practice this probably in the next class more. But Hadi, remember, you're going to focus on one atom at a time. So let's focus on this nitrogen atom. It's got 1 lone pair, and focus on the central atom, right? So it's got 1 lone pair and it's got 3 bond pairs, right? So it's going to somewhat look like this. That there's going to be 1 bond. It's going to be like a pyramid with a lone pair sitting on top, right? And there are 2 hydrogens. And then there's this carbon on this side. So Ani, at this point, that's the first part. We've drawn this part, right? Then we move to the next carbon atom, right? The next carbon atom is fan-shaped because it's just got 3 pairs of bonds. Like it's 1 pair over here, 1 bond pair, 1 bond pair. So focus on the middle carbon atom. That's going to be fan-shaped. All the angles are going to be 120 degrees, and it's going to be fan-shaped. Okay, let me draw this like this and make this one dotted. Anya, is this point clear?
Yes, sir.
And then you move to the next carbon atom. That is tetrahedral. So that means it's going to be like this. Around that carbon atom, the arrangement would be tetrahedral, and all the angles would be 109.5 degree. So the molecule shape would be like this. It's going to be, the first one is a pyramid. This N over here is a pyramid. The next carbon atom is trigonal planar. It's fan shaped, so it's like a fan. And then last carbon atom, it's got 4 bonds, so that is tetrahedral, and all the angles are going to be 109.5. So we'll focus on the shapes. We'll do more questions on the shapes. Okay, we've drawn most of the shapes. Okay, they're all here. And we're going to focus on the shapes. We're going to practice some questions, a lot of them, to figure out to get this right. Like if we see a molecule, and remember, this is not the shape of the molecule. Whenever you see a structural formula, it just shows you which atom is bonded to which atom. It does not show you the actual shape. Like the carbon, I mean, we drew the hydrogen at the bottom. That is meaningless. It just shows that hydrogen is connected to this carbon atom. It does not show how the hydrogen atoms are actually in reality arranged around the carbon atom. Okay. So in the next class, we'll practice these shapes. Okay, we'll learn how to practice the shapes of the molecule and figure out the shapes of each molecule. Whatever molecule we're given, we should know how it looks like in reality. Okay. So we'll continue this in the next class then. Okay. Okay. Quick question.
Allah Hafiz.
Okay, Allah Hafiz.
Allah Hafiz.